Okay, page 7 of the fault tolerance notes, and we're continuing with the precision time protocol. So the idea is that you've got your local area network, you've got your grandmaster time server. It gets its time from some fairly reliable source like GPS or the cell network, and then it periodically broadcasts a synchronization packet out to all the instruments or computers on the network, and they synchronize to that. So here is a picture of the synchronization sequence. I guess you could call this a protocol. What we've got is the master on the left, slave on the right, and I want a bit more room on the right hand side of this page to draw things. And so we've got time going down the page here, and what's going to happen is the master is going to send a sync message or sync packet to the slave. The master will record when it sends that, so we'll call that T1, and the slave will record when it receives it, so we'll call that T1 prime. How they record this, usually they use some kind of dedicated hardware to do that. It is possible to do it just using software in your standard Ethernet port on a computer, for example, but then your accuracy goes down and you're talking in the neighborhood of, I think, tens to hundreds of microseconds instead of, tens of nanoseconds. So there's a cost to that. And the slave needs to know what time the master sent that, what time the master says it sent it, what's the value of T1. So T1 might be part of the sync message, or it might be part of a follow-up message. So I'm doing this dotted. So older hardware would send this follow-up message with the T1 timestamp. So it would measure as it was sending the sync message, and then it would send a follow-up packet with the value of T1. Newer hardware is able to do both at once, to embed the timestamp in the sync packet itself. So let's put that into writing. So sync may contain timestamp T1 and follow-up is optional. It contains T1 if sync did not. And whether or not sync can contain the T1 is just a matter of the capabilities of the timestamping hardware. So now the slave has an idea what time the master thinks it is, it has an idea what time it thinks it is, and it can do a correction based on that, but it doesn't really have a good measure of the delay in sending the message, and it needs to figure out what that is. So they do something clever here. Networks, it depends on your network, but messages sent from one computer to another or one device to another can take varying amounts of time based on congestion, the current state of the network, that kind of stuff. So the slave at time T2 is going to send a delay request, and now that I look at it, follow-up should have been an underscore, not a dash, so follow-up in both those places is an underscore. Delay request is sent by the slave, and it doesn't send it after every sync message it gets, but once in a while it will do, just to check on what's the latency on the network. And then the master will record when it receives that request, T2 prime, and it will send that back to the slave. So this is the delay response, and delay response contains the T2 prime timestamp. And that's the protocol. So now we can actually work out what the slave synchronization error is, and also what the delay was in the network. So what we have is the slave knows T1, which comes from the master, T1 prime, which was measured at the slave, T2, which was measured at the slave, and T2 prime, which was measured at the master. And we can write out a couple of equations. So T1 prime is going to be equal to the authoritative time T1 plus whatever error the slave has, its synchronization error. So let's write that. So this is the slave sync error, just how much its clock is off by, plus L. And L is the network latency. And we can create a similar expression or equation for T2. So T2 prime, the time that's recorded at the master, will be equal to the time that the slave says it sent that packet. And in this case, because we're going the other way, we need to subtract the slave's synchronization error away. And that should give us the time at T2, plus the latency again, because the packet's going across the network. So now we can restate each of these in terms of the synchronization error. So delta from the first equation is going to be equal to T1 prime minus T1 minus L, and from the second equation, delta is equal to T2 minus T2 prime plus L, and we can combine or add these equations. So we can have 2 delta is equal to T1 prime minus T1 minus L plus T2 minus T2 prime plus L. And so the L's cancel each other out, and we end up with this equation. Delta is equal to T1 prime minus T1 plus T2 minus T2 prime all over 2. So delta is the correction factor for the slave clock.